What is this? What do you mean? Okay, my name is Zaitsev. I'm not Peter's brother, by the way. And I will be talking this. And I will be talking today about the foundation, about what we do with Altinity, ClickHouse, and data lakes. What is Altinity? Altinity is ClickHouse shop. So we're first commercial vendor for ClickHouse since 2017, and still an alternative to ClickHouse. So we're doing ClickHouse development, ecosystem development. Usually is responsible for a lot of ecosystem projects, and also we're trying to move ClickHouse to some new use cases that we see from our users. And I will be talking about one of such use cases today. But before then, let's talk about innovation. How innovation actually happens in the industry. It can be incremental when you add small pieces here and there and improve your products or improve user experience. It could be revolutionary when you came out with something completely new, which changes the way that how users do their business. Sometimes small incremental changes, they accumulate to a critical mass, and that leads to revolutionary change. This is mechanics. What is the source of innovation? You should listen to users. And what we're doing, always listening to users, so we're trying to understand their needs, and that drives what we're trying to do. Of course, there are some revolutionary people like Steve Jobs that can invent something that everybody on the planet needs, but we know about Steve Jobs, we don't know about even other people who try to invent something that didn't fly. So listen to users, and this is what we did. A few words about ClickHouse. I know that some of you know what this ClickHouse is, and maybe more of you know after using tools. But this is the analytical database for real-time analytics. It's not MySQL, it's not Postgres, it's not for all. It's for scanning huge look at the same data. They have to go to the same ClickHouse instance. They cannot run different ClickHouse and look at the same data. This is another problem. So usually your ClickHouse system is way over provisioned for compute because you want to give resources to everybody who wants to use the system. So what users really want, they want to scale compute separated from the storage. This is called the compute and storage separation. If they need some more resources or new use cases, they just run more compute for that. And also they want to use not just by ClickHouse, but some other tools like Iceberg, for example, or some others machine learning tools. Now let's think a little bit about why ClickHouse is so fast. So ClickHouse is famous for speed, and this has a lot of different optimizations. Some of them are listed here, and it would took me several hours to explain how they work. But they were all designed with very smart people for speed. So every change in ClickHouse is always tested for speed. And if you want to change ClickHouse in a way how users want, they always ask, whatever you do, keep ClickHouse speed. It should be as fast as now or faster. Don't make it slower. So we have goals for user demands, object storage, shareable format, so we can share the data, not just with ClickHouse, other tools, compute storage separation, and real-time ClickHouse speed. So we need to keep it. How to solve this problem? It's not trivial. Let's look into merge. So merge is a table engine inside ClickHouse which stores data in columns. So in Postgres or MySQL, we typically store in rows. There is green column and with columns, but this is kind of exception. ClickHouse stores the data in columns, which makes it very efficient for players who can only pick up several columns from the table, and also it helps to compress data quite efficiently. We have people who migrated from Postgres to ClickHouse with 100 times more cost reduction on storage, because data just it is compressed 100 times thanks to volume storage. But if you look into that, it's not just ClickHouse can do it. There is Percona, which does exactly the same. It's not a table format. It's just open format, file format, which is totally open source and understood by many systems, and it can do exactly the same as MergeTree does. Also, there is Iceberg, which is, so if you have files, but the files, you need to organize them. And there are tools to do it. One of them is Iceberg, which helps you to organize data on the screen. It exposes this data as tables using so-called catalogs. And these catalogs can be used by many applications that connect to this data, and they see the same data, they run the same queries. It's open source, but it's not a database management system. It only can provide the information about the data, but you need a tool to query this data. So Parquet and Iceberg gives you almost everything. It is cheap, columnar, with partitioning, with a lot of features that databases may have, but it doesn't give you a query engine at all. You may guess that what we're doing, we're trying to use ClickHouse as a query engine for Iceberg and Parquet. And this is what our project entirely does. So that was the source of innovation. Now we are trying to make innovation inside ClickHouse. We are extending ClickHouse native capabilities with some new features that allow us to use Iceberg and Parquet for shared storage. Additionally, on top of that, we are also extending ClickHouse to run stateless compute nodes, which are called swarms, that can be used in order to scale the compute for Parquet independently from your main ClickHouse cluster. So let's check those features one by one. So this is our swarm execution model. As you can see, the query on the right side, it goes to the initiator native ClickHouse cluster that you may deploy years ago, it contains some data. But when you need to query Iceberg and Parquet, you can additionally launch this what we call swarm cluster, which is stateless. It doesn't give any data at all. Its only purpose is to fetch data from Iceberg, Parquet, as object storage in the most efficient way, do some pre-aggregation, and then return data back to the initiator to provide final results to the client. It is totally stateless and new execution model. Sometimes I like one of the first slides on this, when you where the swarm concept goes from. So imagine it's a lake, right, with a lot of data, and you have a swarm of bees which is coming to this lake and take the water and bring it to your ClickHouse gateway. And there is a man, beekeeper, who is responsible for the swarm, just to manage this data and make sure that nobody will come. How it works, so this is SQL, it's ClickHouse SQL, and you have a query that queries data from the public history bucket, and in order to extend it to swarm, you just add a setting. You don't need to rewrite the query, just add a setting, and it will automatically offload the query to your swarm cluster. So you don't need to do any changes to the main cluster, just offload using settings. And similar for Iceberg, so this is how to configure Iceberg database engine in ClickHouse, and once configured, you can query it the same way. But in case of Iceberg, your tables in Iceberg, they look just as a regular tables in ClickHouse, but you can extend them to the swarm as well with a setting. This is very powerful execution model. But it doesn't work out of the box, so we had to add a lot of caching layers. Because object storage was slower. If you have data on a local disk, it's very fast to read. If you have data on network, you need to go to network. And in object storage, you have a latency not just for streaming data, but also for connecting for the network, especially if your bucket is in different region. So we introduced a number of caching layers that help us to reduce this latency to very reasonable levels, and guess what? When in a simple performance test, and this is a setup, like you have a data set of 1.3 billion rows, pretty common one, very simple queries, and if you run those queries on native ClickHouse and on Swarm, you can get performance on Swarm better thanks to additional compute that you can provision. So, and it will be even better with new ClickHouse version because it introduced the better Parquet reader. This is proof that with this architecture we can actually make ClickHouse, keep ClickHouse performance, but use the different storage model based on open table formats. one more thing that we had to do is catalog. So catalog is a service which exposes data in a table form. And apparently there are many catalogs, but not too many to run in Kubernetes. We only found one, Lakekeeper, which is quite popular right now, written in Rust, but all other options they just import. So we had to develop our own catalog, which allows us to deploy it in any Kubernetes environment, in our own cloud, in user environments. And this catalog can then be used as an entry point for external tools like AI or whatever, and for ClickHouse as well, for some clusters. Next stage. So once we have this architecture, we need to think how to make it work better for ClickHouse. So we have some data in Iceberg, some data in Washington. How to make things to look the same data for the end user. And this is what Infinity table concept is for. This is kind of, you can imagine a super table which is smart enough to understand that part of your data, maybe your recent bits of data are stored in fast Washington tables, but your other data, your whole data, historical data, years of data is stored in Iceberg. And this Infinity table, it automatically rolls a query. ClickHouse already has such functionality internally. The rolls the query accordingly. Parts of the query goes to one storage, and another part of the query goes to another storage. And the results are merged and returned back to the user. And from the user perspective, there's no difference. The user just queries the table, and all the logic is happening inside. And as you can see, the part of the query is executed immediately on a local machine, but another part of the query is executed on a swarm of machines. Again, we are making it in order to make it fast. And the next step, which is still in plan, so we're working on that, is to implement double write. We were talking about real-time data lakes at the beginning, and we will finish with that at the end. But you know that real-time is actually two sides of the coin. You need real-time queries, and you need real-time ingest. ClickHouse is very good for real-time ingest, but not Iceberg. In Iceberg, it is very, very slow, very, you cannot serve data too fast. That's why we originally were writing data to native ClickHouse and then offloading it to the Iceberg. But we're also working on double write architecture that would write data in two storages automatically. And the Infinity table, it already understands the semantic, it understands which data is called, which data is called, and can automatically select it in a query. But in this case, we also have the real-time ingest, and the query is available immediately. But this is a data lake. This is, in fact, this is a real-time data lake, real-time ingestion, and we're doing real-time queries at the same time. So this is what we were trying. We were not trying to build it, but eventually, after small increments addressing user needs, we ended up with real-time data lake architecture, which is something really, really cool. This is all open source, so everybody can use it. If you're good with Kubernetes, you can run it. We have GitHub repository with examples. There is a Terraform in order to set up a EKS cluster in AWS. And everything else is managed by Kubernetes manifests. So you can apply this as number of manifests, and it will stand up very trivial ClickHouse node and ClickHouse swarm cluster that you can use in order to run examples that I just demonstrated. So it really works, and we hardly work to make it better. We also deployed everywhere using Altinity cloud stack. I don't have time to talk about that in detail, but in general, what we can do, we can deploy the cloud infrastructure and Kubernetes infrastructure in any location, in any account. It could be AWS, GCP, Hetzner, DigitalOcean, but this part is not a process. It just makes things easier for users. Some resources that you can read if you're interested, and that's it. Thank you very much. Yes, question?
Hello, Zero.
We use what AWS provides for GCP. I think it's currently, I don't know what kind of hyperscaler they use internally. They deploy containers inside clusters right now, but it doesn't. The hyperscaler doesn't directly influence the data size because typically you need more compute for more data. So per one CPU, you cannot process more than X amount of data just with the limitations of the CPU. So when we're talking about petabytes of data, we're talking about clusters with hundreds of nodes and hundreds of CPUs. And this maybe a bit of extra penalty which hyperscalers can give, it is neglectable at this scale of things.
I see. So in other words, you're letting your customers bring their own cloud?
Yes.
Yeah?
Yes.
Okay. I see. I thought it was you know, partner with the hyperscaler, and then the customers would just pay for the infrastructure.
No hardware appliance. Of course, we can give SaaS service, but it is running absolutely the same application stack of cloud stack as we do for our customers in their accounts.
I see. Okay.
Because appliances are hard. They're hard to manage, they're hard to maintain, and they may get older as the hardware gets older. So we're just trying to be as universal as possible. If customer has some unique hardware, fine, they can use it.
And the other question is so we're seeing here and there in the slides S3 connectors, and my question is do all of the hyperscalers, they support the same protocol, or do you have some things around S3?
S3 protocol is standardized, so we use S3 protocol for AWS and for GCP. So GCP has a good implementation of S3 protocol. Azure is a different use. Azure has its own API to object storage, and for Azure, ClickHouse has its own implementation of connectors and stuff. But it is underneath. The iceberg itself, it is cloud agnostic. So it just needs to know how to connect and it returns paths to files to the query engine, and if query engine can access this path, then it can query data. Yes. But S3 is very popular. For example, I think Cloudflare has S3 compatible object storage. Even Hetzner is kind of S3 compatible object storage. So this is the fact standard.
Yeah, so there is a layer of abstraction in the
Yes. Minio is used in on-prem quite often.
Okay.
Other questions? Everybody's tired. Okay, thanks. Let's make it short today.